Alright guys, I'm gonna start off with making a few videos this year for each of my courses. I have a few courses left to complete in my degree, and I'm gonna be making some kind of like tutorial videos because for one, it's helpful for me to go over the material, and secondly, I like to help out my friends that are having trouble with concepts in class. These videos are very easy to understand in my opinion, so I'm just going to be going over basic questions, and I'm going to start off my videos today for the fall semester with ECIV4230, which is Civil Engineering Analysis. This course stems on the knowledge that we learned in calculus, and the first few assignments test our calculus skills and finding particular and complementary solutions and general solutions for differential equations or higher order differential equations. And today I'm going to be solving a couple examples of a homogeneous second order differential equations, and I'm going to be going over for these first ones are homogeneous. We're going to be finding the auxiliary equation, and then we're going to be solving for our roots, and we're going to have a few different cases today. We're just going to be solving for those. So I'll start off by writing the first one. We're going to be using this one right here. We have y double prime minus 36y equals 0. So right off the bat, if you don't know what a homogeneous equation is, homogeneous equation is a differential equation that equals 0, and if your differential equation doesn't equal 0, to find the complementary solution, you always need to have it equal 0. So if you don't have it to equal 0, let it equal 0, solve for the complementary solution, then move on to solving for your particular solution, which we'll discuss in another video. So the key with these questions is that you have to realize that you have to find your roots, and I'm going to write a few things down and then I'm going to explain. So for these questions, there's a proof that's in the textbook that we discussed in class as well, and basically we're just going to be finding a solution or a root that works for this homogeneous differential equation of the second order. So a few things you got to keep in mind. The first thing is that if you have sorry, I'm just going to adjust the light here. If you have a solution, what always ends up happening for the most part is that you have y equals e to some root mt, and then if we want to differentiate this, y prime will equal me to the mt, and if you want to differentiate this again, you'll have y double prime equals m times m, which is m squared e to the mt. Okay, so you have to realize this if you want to go over the background of this, which I'm not going to go over in this video. It's in the textbook, so take a look in the Advanced Engineering Mathematics textbook for higher order differential equations. I believe it's chapter 3. So it explains in depth why we use this for our calculations. So at this point we can plug our differential equation differentiation into our original equation, and this works out to be a solution each time. So let's go ahead. We have y double prime, so I know that y double prime here is going to be m squared e to the mt, and I have a minus 36, and then I just have a y. My y I know is e to the mt, and I know that equals 0. So these are the building blocks for our auxiliary equation, and I'll explain what the auxiliary equation is next. So if you look at our equation, our new equation that we've created here. We can factor out e to the mt, so we'll do that. Factor out e to the mt, and we're left with m squared minus 36 equals 0. So this right here is going to be our auxiliary equation. Auxiliary equation. A lot of people call it a characteristic equation, but basically it's the equation that we use to solve for our roots, and it's helpful when we're dealing with a homogeneous differential equation. So if I rewrite this as m squared minus 36 equals 0, I can solve for my roots by simply doing this, 36, and then I'll take the square root of both sides. I'll get m equals plus minus 6. Meaning I have two distinct roots. I have a positive 6 and a negative 6 for my two roots. And I'll write them right here. I get m1 equals negative 6, m2 equals 6, because I have m plus 6 equals 0 and m minus 6 equals 0. You have those, so m1 I'll go as negative 6 and m2 as positive 6. So in this case I have two distinct roots, and when you have two distinct roots, you can basically write out your complementary solution in the way that each one is distinct, and you don't have to do any other magic tricks or anything to get to your final answer. Y equals yc plus yp. We'll get into yp in a different video, so we don't have yp in this solution. We just have our complementary equation, our complementary solution, which we found using the auxiliary equation. So in that case, our solution is always in the format for the yc. In this case, our general solution is going to be equal to our complementary solution, because we do not have a particular solution to solve for with undetermined coefficients, which we're going to solve for next. It's going to be equal to, we always have an arbitrary constant c1, then we have e to the m1t, and then we have our next solution, which is distinct. We can add another arbitrary constant, e to the m2t. So our final answer in this case is going to be equal to y equals an arbitrary constant c1, e to the negative 6t plus c2e to the 6t. So that's the solution for that one. And as you can see, this is just one of the first problems in the course, so it's not too difficult. And I'm going to solve one more in the next video.